Good morning, my friends. You can do better than that, Mike. Oh my, I think we need more coffee. There's plenty of coffee there, so make sure you get that. Welcome to the 12th Annual University of Chicago International Education Conference. So who is feeling inspired this morning? That's better, I like that. So who's ready to delve into one of the most pressing issues of our times, the hot topic, global climate change? No, we definitely need more coffee for that. Okay, so I myself am feeling inspired to be standing in front of a room full of colleagues and educators who are dedicated to expanding horizons and engaging with global issues that impact all of our lives. While we may face daunting challenges such as climate change, I feel confident that together we can accomplish many great things. So my name is Abby Newman, and I'm the Associate Director of the Center for East Asian Studies at the University of Chicago. I'll be serving as your MC today at our International and Education Conference, and I look forward to working with all of you. Thank you very much for participating in this important professional development activity and opportunity. While I physically may be standing up here in front of you, I do not stand up here alone, as this event was made possible by the hard work of a team of colleagues from the University of Chicago International and Area Studies Centers. So I'd like to take a moment to point out my dear colleagues and remind you all that we are here to be resources for you, both during and after this conference. So should you have questions about a particular world region, if you're interested in learning about additional materials, you want to get more involved or sign up for our mailing lists, or just learn more about our events, please keep these friendly faces in mind. From the Center for East Asian Studies, my colleague Connie Yip is our Assistant Director for Programming. From the Center for East European, Russian, and Eurasian Studies, say that 10 times fast. We all have acronyms. We have lovely acronyms. So Center for East Asian Studies is CEAS. And CERES, the Center for East European, Russian, Eurasian Studies. We have our Associate Director, Esther Peters, and then behind the camera, Matthew Weflin is the Outreach Coordinator. And from the Center for Middle Eastern Studies, or CMES, we have Thomas McGuire as the Associate Director, and the Outreach Coordinator, Krishna Kulkarni. So we'd also like to extend our thanks to additional program sponsors, the University of Chicago International House Global Voices Program, the Neighborhood Schools Program, and the Office of Civic Engagement at the University of Chicago. This conference is also made possible through grants from the Title VI National Resource Center grants from the U.S. Department of Education. Before we get started, I have to go over a few housekeeping items. So, folders. Everybody should have these delightful navy blue folders. These contain important information such as the schedule, the bios for presenters, resource lists, and lesson plans. Wi-Fi information is also contained in your folders, but also is posted on flyers on the walls here. So for those who have not yet connected, the wireless network is UChicago-guest. The username is 2019IEC. IEC is all capital. And the password is global with a capital G. Phones, please silence them. Bathrooms, everyone needs to know if you haven't visited them already. They are located out the doors of this assembly hall, and on the left is marked for women and the right is for men, and you take the stairs down to the restrooms. Evaluations. So at the end of today, we will take time to complete evaluations together as a group. One is University of Chicago evaluation, and the second, for those that need it, is the Illinois State Board of Education evaluation forms. So for those that need those, that would be for continuing education and professional development units. So when you hand in your ISBE evaluation, you receive a form as evidence of completion for professional development. So we thank you in advance for taking time to complete these evaluations and surveys, because they're important feedback mechanism that helps us to craft programming that meets your interests and needs in the classroom. So thank you in advance. In addition, you don't come away open-handed. Besides all of the lovely knowledge and resources and information and new connections that you make, you will also receive at the end of this conference a lovely certificate of completion from the University of Chicago that you can proudly display in your office and make your colleagues jealous. So just want to make sure you're all aware that that's going to be handed out at the end. And finally, as a reminder, we have the presentations, links to YouTube videos, and additional resources for past events and for everything that we've worked on. They're posted on our recently launched UChicago Educator Outreach website. And you can search the site. We're really pleased. You can search now by keywords to find materials. You can view the materials from past programs and other campus resources. So if you don't already have this on your bookmarked on your browser, please make sure that educatoroutreach.uchicago.edu is on your list. So we will send out a notice to have all participants when the materials from this International Education Conference are available and when they're posted. So we'll always keep you in the loop. Do we have any questions so far? Great. So over the course of the day, we will explore how to consider the methods and topics for teaching climate change, both to STEM and to non-STEM students. We have a group of distinguished speakers who will approach the subject from a variety of perspectives, from cutting-edge science, classroom demonstrations, political science and economics, and social justice. We want to inspire connections for today and for tomorrow, whether it be professional and interpersonal connections, materials and resources to consider connecting in your classroom, curricula, or institution, or bringing issues of global climate change closer to home. We hope you will come away with some inspiration and resources. So as we embark on our journey exploring humans and Earth's carbon cycle, interdisciplinary approaches to teaching climate change, methods of combining physical science with social science in the classroom, developing global perspectives on efforts to combat climate change, and the impact of climate on society, and society on climate, we hope that the presentations, discussions, and resources will provide inspiration for you and your students, and that you leave with experiences to bring back to share with your colleagues, schools, and communities. So now let's get our fabulous program started. Yay! So our first speaker, David Archer, is professor in the Department of Geophysical Sciences and a scholar with the Energy Policy Institute at the University of Chicago. He works on a wide range of topics pertaining to global carbon cycle and its relation to global climate. He teaches classes on global warming, environmental chemistry, and global geochemical cycles. Professor Archer also offers a free open access online class on global warming, the science of and modeling of climate change, available on Coursera.org, and the links are also available on his departmental website. He's author of numerous publications and books, such as The Long Thaw, How Humans Are Changing the Next 100,000 Years of Earth's Climate, and Global Warming, Understanding the Forecast. Professor Archer is also a contributor to the website realclimate.org, where commentary written by working climate scientists can be accessed by journalists and the public. We are very fortunate to have him here today, so without further ado, please join me in welcoming Professor Archer to the stage.
Good morning. Welcome to Chicago. It's a little cooler here today than usual, but the weather here is always beautiful. So I am a computational carbon cycle guy. And back in 1995, I collaborated with another professor here who was an atmospheric dynamics person to build a class as part of our core curriculum, meaning for non-science majors, you know, they have to take at least 2 classes in the physical sciences. And we wanted to put together a class that would, there's a weird echo in here. Are you getting that? I guess it's just the room. That would start from complete naivete and try to excite the students' sort of sense of wonder about the natural world. So what is heat, and how does light carry heat energy through the nothing between the 93 million miles between here and the sun? The black body spectrum is a product of quantum mechanics, and nothing is weirder than in this world than quantum mechanics. So it was kind of a nerd's kind of approach where we would try to excite their sense of wonder, and then, you know, gosh, isn't the atmosphere cool? Isn't the carbon cycle amazing? And then sort of sneak around behind them and say, wham, there's global warming. And so the guy who's taken over doing this class now is sort of crossing the same bridge, but in the opposite direction in the way he's developing it now. He's sort of banking on their students' concern about global warming to try to get them to think about science and to think the way a scientist does. So it's kind of like crossing the same. Maybe my approach was sort of a defensive crouch, although I never had students try to, you know, debunk me actively. They would just argue about grades or whatever. So anyway, I put a lot of work into creating resources for my and other people's classes. And so what I'm going to do this morning is stand up here and shamelessly hawk my wares in the hopes that some of it may be of use. I'm going to sort of give you a quick tour of how we did the class and how it worked. I hope if you have questions, you will raise your hand and ask while we're here together, rather than sitting there politely and letting me blather on. So there's a textbook for the class. Here is a sample page from the Amazon page, so you can kind of see what level I'm going for. You know, there's a light wave and a wavelength and whatnot. I was trying to start from like absolute sort of nothing. Part of the whole package is a series of interactive models, computational, like research grade numerical models of different parts of the climate system, which are all available on a server for everybody to look at. And a lot of the homework exercises in the textbook are based on using these models. These models are available for anybody. There's no logging in or anything. They're just there. If you're teaching a class and the thing is down, give me an email. I'll try to get them back up again in time. So I'm committed to keeping these going. So I'll show you some of these as we go. Each of these pages has sort of see the more on this model link up there. You go to that and there's a video of how the model works and a little things to do thing, which sounds better than homework assignments, but it's ideas of things that you can discover or have your students discover in these models. I put together a MOOC, a massive open enrollment online class on Coursera.org. So they start a new session of this every month. And to do that, I had to make videos of the material. And there's a page, this is a picture of a page that has videos that go with the chapters in the textbook, both in a classroom sort of 45-minute lecture format. I just had, you know, TAs run a video camera as I was teaching one year. And then when so I made a kind of homegrown MOOC out of these long time ago, and then when the university signed on with Coursera and they let me make a Coursera class and get, you know, tens of thousands of people, they like videos that are sort of short, like 5 to 10 minutes on you know, particular topics. And so, you know, they're available in both formats there. So the way the class starts out, I mean, we do heat and light and the black body spectrum and to start out with, like I mentioned. But then there's a simple model of the greenhouse effect, which I already had my PhD, and I didn't understand how this worked until I was prepping to do this class when I saw this model. So to start out with, you have a planet, and you're getting sun energy coming in at some rate. The rate is 1 minus the albedo, which is how much gets reflected out to space, times how bright the sun is here. And then the factor of 4 is this amazing conversion between the area of a circle, which is what the sun, how much sunlight gets intercepted is a circle, the size of the Earth's shadow. And then the energy leaving is from the whole planet, and the area of a sphere is 4 times bigger than the area of a circle. Well, that's amazing. Because pi is a transcendental number. We can't even calculate it exactly. And yet the ratio, right? Isn't this cool? Yeah, so anyway, this is a story problem. There's one unknown, it's the temperature of the Earth. And you can calculate what it is, and it's way too cold to represent the average temperature of the Earth. So then,
can you calculate the albedo, or does that have to be taken as an input factor?
It depends on all kinds of climate-sensitive variables like clouds and snow. And so it's actually kind of an interactive part of the climate system. The albedo of Mars is like half what the albedo of Earth is. And the albedo of Venus is like twice what ours is, because it's like always cloudy on Venus. So it's kind of an interactive variable.
So is the albedo being modified in the climate change? Is it different in this anthropogenic epoch than it was in the Holocene, the albedo factor?
If the clouds change, or we melt a lot of sea ice, then the albedo will definitely change. That's kind of an issue. Melting the sea ice in the Arctic, in the northern polar region, is a huge albedo change. And it's kind of dicey because it's right where you make deep water in the Atlantic, and it's also where the Greenland ice sheet is, so that's kind of a bad place to mess with albedo. Anyway, so to rescue our planet that was too cold here, we can put sort of a pane of glass above the surface, say that the sunlight goes through the glass without being absorbed, but all the infrared gets absorbed by the glass, and then the glass radiates up and down itself. And they're both radiating according to their temperatures, according to the Stefan-Boltzmann equation, sigma t to the 4th, which is the energy in the black body curve. So now we've got a somewhat more complicated story problem with 2 variables, or two unknowns, and you can put together energy budgets for the different parts and solve to get that the pane of glass has the same really cold temperature that the Earth had before. It's called the skin layer, and it always has the skin temperature. This top layer has to put out as much energy to cross this boundary to space as comes across the boundary to space here. So this layer here is always has the same temperature, and then the temperature of the ground turns out to be warmer. So it's kind of like if you have a kitchen sink and you turn on the faucet and the water in the sink kind of rises to some level until you've got enough water in the sink that it goes down the drain as fast as coming in from the faucet. So you get to a sort of a steady state where the water budget is in balance there. And then if you put like a little piece of carrot or something on the drain and it increases the resistance, and then the water level goes to a higher level until you've got more pressure pushing it past the carrot, you come to a new steady state by blocking the outflow. That's what's happening here. You're blocking the outflow of heat, and it requires that the sort of standing inventory of heat has to be higher in order to balance the books again. So a very cool model. But greenhouse gases are kind of more complicated than a piece of glass that absorbs all the infrared and none of the visible. Because greenhouse gases are very simple, and there's only limited ways that they can interact with light. So one thing is that the frequency of the light has to be sort of matched by the frequency of vibration of the chemical bonds in the gas. So, you know, they're sort of picky about what frequencies they can absorb and emit. The other is that when you do the vibration, you have to make an asymmetry in the electrical field called a dipole moment. So if you have oxygen, for example, that's symmetrical, two oxygens, they're the same, they're always the same, there's never an asymmetry, no matter how you vibrate them or whatever. So oxygen is not a greenhouse gas. It's not what we call infrared active. Carbon dioxide is symmetrical in its resting state, but there are modes of vibration. There are different modes of vibration here that have different frequencies. It's like a musical instrument that plays, 3 notes at the same time, if you could hear it. And some of those vibrational modes break the symmetry, like this bend. So when you're bent this way, the oxygen is sort of negative, the carbon is sort of positive, so you have an electrical gradient this way, and then it reverses and goes back and forth. So when you put...
How do you get an asymmetric stretch when it's... Why do you get an asymmetric stretch when both are, C double bond O and it's a linear molecule?
It looks like this. Does that answer your question? You have to, the way I explain this is a vibration on a bunch of atoms like that has to come around and recreate itself, kind of like an ocean wave recreates itself. That's the shape that propagates, or a light wave. So an asymmetric stretch, it goes like this.
No, I understand how it goes, but what is driving the asymmetry? Both are double bonds, and it seems to be a symmetrical linear molecule.
Oh, this is a deep question. This is a great question.
The polar, the polarity is going in opposite directions. So oxygen is more electronegative. What is driving the asymmetry? That's my
the thermal energy of the CO2. These gases, if they were at absolute zero, there'd be very little motion. Actually, there would still be some vibrational motion. The bottommost quantum level for vibration is not zero, which is weird. But they are at temperatures above that. They're constantly getting clobbered by collisions with other gases. And so, they have this energy, which is, defined as the temperature, which is how much kinetic energy they have. So they're flying around, and all of these different modes will have, on average, the same amount of kinetic energy at thermal equilibrium. So it gets excited to do this just because it's gotten clobbered, and so it's just doing all of this all at once. And doing this is one of the high points of the class. The students loved that. And then so here's the bend, and here's the symmetric stretch, right? I can't do methane because I only have 2.
But all of these are happening all the time.
Yes.
Those are snapshots of still, and that never happened. That picture right there, they move through that state.
Yeah, they don't stay like this. They're doing this with a frequency, right? It's like guitar string is never bent all the time because it. So if you put these choosy greenhouse gases into the context of the infrared light in the atmosphere, you get a picture like this, which is a spectrum of the energy that leaves the Earth from space. So these curves here are smooth black-body curves corresponding to different temperatures. And if there was no atmosphere, in fact, in this model, you can put the little virtual sensor right down against the ground and see what's actually leaving the ground, and it's a smooth curve like this. But as the light is going through the atmosphere, if it's being absorbed by carbon dioxide, the intensity goes down, because what you see when you look down from space is air that's high up, and it's much colder than the air at the ground. So if you had a cloud that was at this temperature, you'd have a black body curve like that, because a cloud can absorb and emit all the different frequencies of infrared. So we have this sort of composite picture of, it's like a thermometer that sees different parts of the atmosphere. Right here, this is called the atmospheric window. You're seeing the ground pretty much. Here's the CO2 band for the bend, and you're seeing cold air at the top of the atmosphere.
What's your take on the relative greenhouse potency of CO2 versus methane? Does the fact that methane has more degrees of freedom indicate that it's more potent greenhouse gas, or maybe not necessarily?
That's actually where we're going next. Astute question.
Yes. I teach 7th grade science. I'm trying to explain to 7th graders. Is the peak intensity of infrared light closer to CO2 than methane's absorption rate or frequency?
Yes. Okay. Methane is sort of down here. So CO2 is where the light is, so that kind of gives an advantage to CO2 as a greenhouse gas. But there's something that happens. So this web page lets you put in what the concentration of CO2 that you want, and it calculates what this should look like. And here are 4 different simulations from that model. So there's no CO2. You get, the atmospheric window kind of continues through there. You put just a little bit of CO2, and you get a pretty big peak. And the total energy, the watts per square meter, which is what drives the climate, is it's proportional to the area under this curve. So if you take a bite out of it, that's like putting a carrot on the drain. You're decreasing the energy leaving the space, so the water going down the sink. So then 100 ppm, 1,000 ppm, what you may be able to see is that you get a huge bang for your buck when you first put gas in there. But as you put more and more, it's sort of getting fatter, but it's not really getting any deeper. So this is called the band saturation effect. Band meaning frequency of light, and saturation meaning it's gotten as low as it can get, and it can't get any lower in that center. So what that means, if we look at the infrared energy leaving to space, the watts per square meter of energy, as a function of the greenhouse gas concentrations, if you had 0 to start with there, and you add a little bit, you make a big change in the energy, and so you get a big climate impact. And then as the concentration gets higher and higher, this kind of gets less and less, steep. It doesn't ever go to 0, but it gets less important or less sensitive. So comparing CO2 and methane to your question, CO2, we already have a fair bit. And so the slope looks kind of like that. It's like the climate sensitivity to a molecule of CO2. Here, for methane, we started out with much less. And so even though methane is absorbing where there's less light, it's not as band saturated. And so molecule per molecule, methane is more powerful than CO2 in terms of the watts per square meter of energy imbalance because of this physics. So remember how we had the skin layer in that layer model was always the same temperature? It got more complicated when we started doing greenhouse gases because some of the light comes all the way from the ground and some comes from high up. But still, you can sort of define an average altitude where the energy leaves to space. And if you put more greenhouse gas in it, you're moving that average altitude to a higher level. So it's like, if there was like a fog, if you could see CO2, down here would be a fog we couldn't see very far, but at some point, looking from space, you could see to some depth in the atmosphere. And if you make the fog thicker, it would be higher up, that where you could see light from. okay? So now the trick is to say that the temperature at that level is like the skin temperature. It only depends on the sun because it has to balance the sun. So we start with a natural world with this altitude, which is the average to space, and then we put CO2 in the air, and so if the temperature profile in the atmosphere just stayed the same, that would move us to like here. But after it has a chance to warm up, which is happening now, this temperature has to be what it was before to balance the sun, the energy balance across the space. So then you take this temperature profile, this how much it gets colder when you go up in the atmosphere, and you project that down to the ground. And so this is where the warming that we experience kind of comes from. So this temperature change with altitude, this heading was supposed to be the atmospheric temperature gradient, is called the lapse rate, which is kind of an ugly phrase that doesn't really carry much information. It's one of those things you have to sort of know. But it's a lot of interesting stuff that goes into what determines this slope. And if something changes about this slope, it could change the temperature of the ground. So the lapse rate is another sort of loose cannon kind of in the climate system. And there's a lot of cool stuff in this that we wanted to blow the students' minds with, if at all possible. So convection is a process that happens when you're heating, like if you heat a pan of water from below, the water right at the bottom will get warm and it will rise up, because when it gets warm it expands and it rises up. So for an incompressible fluid like water, which is a simpler case, you start with a well-mixed, statically stable case, warm it up at the bottom, and that rises up. And either you get a blob that goes to the top like in a lava lamp, or what really happens in the atmosphere is that it mixes on the way up, so it tends to increase the temperature of the whole column when you're doing that. Now, a compressible fluid like gas, when you expand it, it actually cools down. Or if you compress it, it warms up. So like if you fill up a scuba tank in a dive shop, they have to put the tank in a tub of water when they pump the air in, or else the tank will heat up and it'll be high pressure, but then you go out and you put it on and go into the cold water, and the pressure goes down, and you've just gotten shorted on your air, which is bad. So, or you can feel it when you let air out of a bicycle tire or a car tire. If you just poke the little valve, it'll feel cold on your fingertip. So in a compressible fluid, here's the statically stable case. This air, if you raise it up, would have that temperature. So this is well mixed, even though they're different temperatures, which is a weird concept for students to grasp. The internal energy is the same, but the temperature exchanges temperature and work. So then you warm it up at the bottom by the sunlight comes in and hits the ground, and you sort of get something analogous to that. And then the temperature gradient going in the atmosphere up, which is what we're kind of after, is also got some cool stuff in it. Not only does it have this rising and expansion, but when the temperature drops, you tend to make water condense. That's what drives all of our weather. The clouds form where there's upward going air. And when it condenses, there's latent heat. So a water liquid molecule and a vapor molecule, even if they're exactly the same temperature, they have different energies, because it takes energy to sort of break the liquid bonds and become a gas. So if you have this vapor and all of a sudden it decides it wants to settle down and go into the liquid phase, it releases heat, the same heat that you get if you put your hand in a tea kettle. You scald yourself with the steam, because the steam goes to water on your skin and you burn the hell out of yourself. So don't ever do that at home. Okay, so then this is what is setting this lapse rate. Other things that are in the real world important that weren't in that layer model, because the layer model was like the simplest possible model you could have. So it's like a toy to make it, you know, fun and easy to play with. But the real world is more complicated. Another way it's more complicated is it's not the same temperature everywhere. You have lots of sun coming in at the equator, and then it's you know, colder at the poles. And the way that the energy gets carried is by winds and current. Ocean currents and winds in the atmosphere about equally are responsible for carrying energy to the high latitudes from the low latitudes. And it's an important part of, you know, climate. And the cool thing about winds on a rotating planet is this Coriolis force. It ends up with the thing, so here's my rationalization of what the Coriolis force is. I tell them about the Foucault pendulum at the Science Museum. It's got this ring of dominoes or something around it, and you get it going in the morning, and it knocks down a domino every 20 minutes or something. If you did that at the equator, you know, if you got it going sort of north and south, it would never rotate, because it's still like going relative to the fixed stars. Whereas if you did it at the pole, it would just sort of go in something and the planet would go underneath it. So there's different rotation that the pendulum feels depending on the latitude of the planet. And the way this plays out for currents is this weird result that everybody goes sideways relative to the direction that they're being pushed. Like, you know, a hurricane has low pressure inside, and so it's like a hole in the atmosphere. Why doesn't the air just fill in the hole? Because it's going around the hole. It always gets, no, I guess it's going this way. It's getting deflected to the right in the northern hemisphere, so the air just goes around and around. The Gulf Stream in the ocean, the sea level is like a meter higher on one side than the other. It's sort of spread out over kilometers. You can't see it. It's flatter even than Kansas, but it's enough that it's a lot of pressure subsurface, this meter of water pushing sideways, but it makes the current actually go. It's like if you put a marble in a bowl and it didn't go to the bottom, it went around and around and around the bowl. So that's cool. And then the climate impact is quite strongly shaped by feedbacks. If it was only CO2, global warming would not be near as bad of a problem. But when you make the air warmer, more water vapor, more water wants to evaporate, and water is a greenhouse gas because it's asymmetrical just from the get-go, so it's really good at being a greenhouse gas. So this is kind of a thought experiment where we start the 3 planets with, you know, basically no water, and then we let the water evaporate, and as it does, it's a greenhouse gas, so it's going to push it's going to take a trajectory toward warmer temperatures here as the water vapor pressure kind of goes up. And this feedback stops on Earth or on Mars when we hit the phase boundary. So the vapor pressure doesn't want to get any higher than this here, because then you're in the liquid boundary and it makes rain. And then for here, Mars hits the boundary for ice, and so it snows. But Venus started out from a warm enough condition that it manages to shift to avoid hitting that liquid phase field. So Venus, sort of in terms of, you know, a habitable planet, is dead, because the oceans that it had went into the atmosphere, the water gets blasted apart in the upper air, and the hydrogen goes to space, and it's lost forever. So, you know, looking at those pictures of the Earth from space and thinking about all that water you can see just underneath this tiny, tiny layer of air, and it's been there for billions of years, it's just incredible that it hasn't done this. On long time scales, the climate of the Earth is set by this geochemical carbon cycle called the weathering CO2 thermostat. So we have CO2 goes from the solid Earth to the atmosphere, the fast carbon cycle. The atmosphere and the ocean and the biosphere, the trees, are considered the fast carbon cycle. CO2 comes out of the solid Earth, to that from volcanoes and hot springs in the ocean. And it finds its way back into the solid Earth by reacting with igneous rocks that have a chemical component of calcium oxide in them. And so the calcium oxide plus the CO2 form calcium carbonate that gets deposited on the seafloor from little critters that make shells and corals and things like that. And then this can be subducted into the earth where it's hot enough that this calcium carbonate is going to get cooked to turn back into igneous rocks again. And that's where the CO2 comes from to complete the cycle. So the thing about this cycle that's cool is that the rate of weathering here, how fast this happens, depends on the climate of the planet. The more CO2 you have, the warmer the temperatures, the more rainfall is washing over these rocks, and so the more of these rocks that you can dissolve. So it's like this kitchen sink again, where you have an input of something, which is the CO2 coming into the atmosphere, and then you have it going down the drain, which is this weathering reaction. And how fast it goes down the drain depends on the standing stock. Like the water in the sink, the standing stock here is the CO2 in the atmosphere. So asking the students, apply the kitchen sink analogy to this, they have a hard time going from, it used to be the sun was the faucet, now the CO2, the volcano is the faucet. It kind of wakes them up a little to use the same analogy for different things, but honestly, it comes up all the time for sort of negative feedbacks. So the bummer about this is that it takes a really long time for this thermostat to act, like hundreds of thousands of years. So there are different time scales associated with the biosphere processing this extra CO2. It takes a couple hundred years, maybe 1,000 to dissolve in the ocean. The ocean gets somewhat acidified from the CO2, which affects plankton and like oysters and things like that, corals. But that acidification gets neutralized as calcium carbonate that already existed dissolves, so it's like eating a Tums or something to neutralize an acid stomach. And then this thermostat takes hundreds of thousands of years. So that's kind of what we're signing on for when we release carbon to the atmosphere. So another one of these online models that you can play with lets you put a bunch of CO2 in the atmosphere, and you can see it going up and taking, this is over 10,000 years, and it never comes back to where it started. And here are the temperatures of the atmosphere and the ocean, and they sort of go up, and you can expand the time scale to hundreds of thousands of years to sort of play with how this looks. There's not a clock in here. I don't know how I'm doing on time. I guess we're okay. Another one of these models lets you play with methane. So this gets back to the question earlier about CO2 versus methane. So we started out, CO2 was the strong one because it absorbs light where the light is. But then band saturation effect, now all of a sudden methane is important because it's, there's less of it to start with. But now we think about the longevity. CO2 lasts for hundreds of thousands of years. Methane basically oxidizes. It turns into CO2 in the atmosphere on a time scale of about a decade. So if you start out with a natural world and you're emitting methane at some rate and degrading it with that time constant, it's like the water in the kitchen sink again. You'll find some level at which you're getting rid of it as fast as you're getting it. But then if we start having leaky fracking wells and put more methane into the atmosphere in a chronic way, that's like turning up the faucet. And so the water level sort of rises to a new steady state on a time scale of, a few lifetimes, so a few decades. And then here, what happens if we have like a spike, a huge release of methane for a few years, you can see kind of goes up, and then it's always trying to go toward a steady state where the degradation is equal to the release rate. So there's another one of these pages that lets students or anybody browse all of the meteorological station data on the planet to look for whether it's really warming up or not. So there are something like 7,000 or 8,000 meteorological stations, and they're given by these little gray dots, and you can select them, and you want to find ones that go back to like 1950 or something like that. And then after you've gotten a few of those, there are buttons to push that will calculate the anomalies, so how much it's changed at each location from the 1950 values. And then you can put them together, and then you can also go through this page has access to climate model results, so you can compare what happened at those stations between climate models where you tell the model about rising CO2 versus other models where you don't. So here it's showing the temperature changes for these stations, and then in the CCSM4 model from those particular grid points, it shows the temperature changes both for the historical forcing, which includes everything, versus the historical natural forcing, which only includes the sun cycle and volcanoes, which are the natural climate forcings. And so you can, if you have the students pick out like 20 or 30 stations from kind of evenly spaced around the world, they'll get the same result as all these, multi-$100,000 studies. Statistically, it's not that hard to see that the temperature is going up and the climate models reproduce that, but only if you tell them about CO2. Here's another one that lets people browse results of the climate models. So here, these are all these models that participated in the last model intercomparison project in 2014, I guess. I'll have to redo this eventually with the new models when they come out. And then here are variables that you can call up and make maps like that. So temperature, humidity, clouds, rain, leaves, soil moisture, runoff, snow, all these sorts of variables. And you can get them for different years. So just by sort of pointing and clicking, you can make a little movie to see things changing, or an annual cycle or something like that. This brings me mostly to the end of what I wanted to show you. I have to run off and teach my environmental chemistry class right after this, and I already told them everything that I showed you this morning, but I wanted to, as a sort of public service announcement, show you what I'm going to show them today, because you might be interested, and you probably haven't heard about this. It's about the element mercury. So mercury, it forms a gas. When it gets released to the environment, the gas in the atmosphere can stay there for like a year, which means that it mixes all over the whole planet before it drops out. It's not a local thing. And then when it lands, if it lands in the ocean, it very likely is going to get recycled back to the atmosphere, or it could go into the ocean, into the deep ocean, and then come back 1,000 years from now and get recycled back to the atmosphere. Or it can get taken up by plants on land, and it can either get recycled back to the atmosphere quickly when the plant dies, or it can be stuck to the organic carbon in soils, which will also be recycled to the atmosphere eventually, maybe after thousands of years. And the only way to get mercury out of the system is by having it buried in deep ocean sediments. So it's very, very much like the carbon cycle in that it has this incredible longevity of the impact. So this figure, I'm going to have a student present this figure in class today, and this is I have them try to pull out the money plot we do sort of a money plot show and tell thing of scientific papers, and this is definitely the money plot of this paper. It's showing what happens to mercury when it's released to the atmosphere, and you see that it goes into these soil carbon reservoirs here, and it goes into the ocean and the deep ocean, but ultimately getting rid of it, it has to go into these ocean sediments, and that's taking sort of 10,000 years or something like that. So it's already kind of dicey to eat higher trophic level seafood as your main protein source. You do that and you'll mercury poison yourself. And we're locking that in for like 10,000 years. And comparing that to the carbon cycle we could at least theoretically clean up, because a large fraction of a fraction of the carbon we've ever released is still in the air. So there are people writing papers, how do we suck this CO2 out of the air? How much would it cost? But for mercury, only a few % of that excess mercury load in the biosphere is actually in the atmosphere. So there's no possible way to clean this up. So, have a nice day. So I think we've got lots of time left. That's sort of what I've got.
I got a quick question.
Yeah.
What's the residence time for CO2? Or should we be using it, idea, to explain to middle school students how long CO2 is out there?
It's tricky, and there has been confusion in that, an actual CO2 molecule might get, turned into a tree and then turned back into the air. Cycling around in the fast carbon cycle is not the same as the climate impacts going away. So the relevant answer is that when we put CO2 into the atmosphere, something like 10% of it will stay in the atmosphere, or an equivalent amount to 10% will stay there for hundreds of thousands of years. You don't want to get confused about sort of exchange versus net uptake. The thing that really has to happen to make it, better is to have it go to the solid Earth, and that's limited by this rate of weathering. A way to scale things is to compare how fast humans are pulling CO2 out of the Earth versus how fast it comes out of the Earth naturally. So it's like we added a second faucet to a kitchen sink, and the human flux is like 100 times greater than the natural flux. So it's a serious faucet. Yes.
I'm a member of the Chicago Sustainability Leadership Network, and we work on various sustainable issues citywide.
Yeah.
And I was wondering if you've spent any time studying the weather just on Chicago and how local Chicagoans can do their part and how universities can do their part to help make the metro area cleaner.
Well, if you go to this Met Station browser site, you can look up the records from O'Hare and Midway and from around here, or you can see maps of temperature change. And the weird thing is that Chicago, nothing has happened. The average temperature is not really changing all that much here, and it's weird because way to the north of us it's changing. Every place is changing. Someplace, one impact that is still being discussed, it's still kind of at the line of scrimmage in climate science, is whether you have more meanders of the jet stream. So the jet stream, it's like the sideways Gulf Stream. It's driven by the temperature difference between the high latitude and the equator. And the way CO2 works, blocking energy leaving, that has the most impact in places that are cold. So you have more warming in the winter and in the high latitudes and at night than you see in the daytime. So the high latitudes are warming and the low latitudes are not changing much. And so the temperature difference is decreasing, which is the force driving the Gulf Stream. So if it's not being driven as hard, maybe it kind of meanders around more. And you get these things called blocking events where something gets just stopped. And those are very serious, like Hurricane Harvey was not a particularly severe hurricane, but it just sat there over Houston and dumped for days. And so that's why, you know, that they got clobbered. So a woman named Jennifer Francis is kind of pushing this idea that there's more blocking events that, you know, that's been kind of one of the main effects on our weather here. Also, Lake Michigan is really high, but I don't know if that's climate change or, yeah, but it's crazy high.
Hi. I was wondering about the mercury pollution. Can mercury be banned? I mean, we have stopped putting it in thermometers, and especially
Yes.
home thermometers, clinical ones, and looking at the dire scene that you painted, I mean, it's a heavy metal that we can just try to totally do without.
Yes, and it has been largely eliminated from coal combustion sources. That was historically one of the main sources, and that has now diminished. And there's a paper from 2017 or something that talked about all these sources. That's the other paper I'm going to have a different student show the money plot from this morning about the sources. And the main source today actually is what they call artisanal gold mining.
Okay.
So they use mercury to dissolve, you know, gold to separate it from the sand or whatever. And artisanal, I guess, means like wildcat, like small scale, you know, unregulated is sort of the main source now.
Okay.
But then in terms of the mercury that we are, you know, that's raining down, that's affecting the sushi and everything, a large fraction of that is what they call legacy anthropogenic, which means it was from gold miners
prior
200
use.
years ago,
Yeah.
and it's deposited and recycled and everything since then. That's greater actually today.
So we can't chelate it or just trap it in such a large scale.
No.
Can't do it. Yeah.
So, you know, to clean the atmosphere of CO2, we, you know, have to process some fraction of the air in the atmosphere on some number of years. But the lifetime of mercury in the atmosphere is only a year. So we'd have to like do the whole atmosphere every year for 1,000 years or something. It's like orders of magnitude harder than CO2. I was right, you were interested in mercury. I wasn't sure, but I thought I would just toss it in.
Does the mercury affect the weather at all? Or is that just an example of the poisoning that you're trying to tell us about?
No, it has no impact on climate.
Okay.
No.
Is mercury a controlled substance? Do you know that? Like for the gold miners that get it, is that something that you have to have a license or something to buy?
I don't think so. It's
Just
weird
curious.
stuff. You see a little bottle of mercury in the lab, and it's like way heavy. It's really strange stuff. But I don't think it's controlled.
One of the practical questions in terms of teaching, you know, you are teaching a whole class based on climate change and all that. Now, I don't have that luxury. I'm teaching a traditional chemistry course, mainly for people trying to get into allied health or whatever, or some non-science also.
Yeah.
So where can this be put in the curriculum and with the time constraints and all that?
Well, I'm sure other speakers today can better address this than I, because I'm not doing sort of a general chemistry class. But there are lots of examples, I would think. You know, I don't think chemistry students learn anything about photochemistry, which is a big deal in mercury and also just in atmospheric smog. You know, or just the chemistry of the atmosphere is all set by photochemistry. It's like the chemistry of a flame. It's really fascinating, but I don't think that is really on the undergraduate chemistry curriculum. And also the idea of steady state, which is more of a natural science, you know, way of attacking things a lot of times that isn't such an important thing in a chemistry lab. So you could try to push, you know, get that perspective across.
I wonder how you think about the carbon sequestration, the version, the process that bury carbon dioxide as calcite, calcium carbonate. Do you think this economically and energetically viable process?
So there's multiple issues. One is where you get the CO2. One option is to capture it from a smokestack, which is energetically easier because the CO2 is more concentrated. To get it out of the air, you have to unmix it from the air. And then another is what you do with it once you've got it. So one option that people talk about is to inject it into geological formations like deep sandstone layers that have salty water in them. So it's got porosity, so you can put the CO2 there and it'll go away, but the water is salty, so nobody wants it to, like irrigate their crops or something. That's one of the biggest geological repositories of CO2. So on the one hand, it's possible that it would fairly quickly react with rocks down there to make carbonates, and so it would stabilize. There are results to suggest that. On the other hand, it's sort of analogous to what they do with fracking wastewater, which, they don't want to, you can't dump it down the drain and send it to a wastewater treatment plant because it's got all these nasty stuff in it. So they just inject it back into the earth, and Oklahoma has earthquakes now. It didn't used to have earthquakes because of fracking. Other options for CO2 sequestration, so either you can make minerals, carbonate minerals like you said on the surface, then you're done. It's not going to go anywhere. Another option is to inject it into the deep ocean someplace, and in that case, some of it would escape, after some thousands of years. Most of the plans that have been put together, the sort of economic plans to stay within a certain temperature target, at the peak, like the Paris Agreement, the aspiration is to limit the warming to 1.5 degrees over the natural value. Most of those plans for how to do that involve what my hero Greta Thunberg calls technology that barely exists yet, that, our generation is sticking her generation with this obligation. There are papers, there's a guy named David Keith who's sort of trying to put together chemical engineering technology to figure out what's the cheapest way to do a chemical removal of CO2 from the atmosphere. And he comes up with numbers like $100 a ton or $200 a ton, which if you multiply that by how many tons of CO2 we are releasing every year, and that we're hoping that Greta will clean up for us someday, it comes to a significant portion of our economic productivity. It's like we're living on a credit card without, acknowledging that Greta has to pay the bills on this credit card eventually. So given that we're already past where we want to be and we're not stopping CO2 yet, cleaning up the atmosphere is that's what I hope for on my optimistic days, but it's not a strategy that's very smart to enter into deliberately. Yeah.
I have a question regarding what you just mentioned about Lake Michigan, how it's very high.
Yeah.
The oceans are seemingly getting higher, and that we think is because of thermal expansion.
Yes.
Is that the same possibly of what's happening with Lake Michigan then?
I don't.
I know that in my lifetime, the average rainfall in Buffalo, where I live, has increased by about 4 inches a year.
Increase?
Yes. So we're seeing more extreme precipitation events and more total precipitation in the Great Lakes Basin overall.
But then there was a couple years ago when it was like much colder than usual, and there was much more ice on the lake, which cut down the evaporation. It's a basic balance between the water that lands. The watershed for Lake Michigan is not that huge, actually, so a lot of precipitation that just lands on the lake, and then how fast it sort of drains out the St. Lawrence. And so, there's questions about whether dredging has changed the resistivity that would make it easier for to drain out. It's not, I don't know. I think it's just like vagaries of the weather.
We recently got out of the Paris Agreement.
Yeah, like yesterday.
Are you aware of any bans that have been reversed in the last 2-3 years, which will affect all of us adversely? Because many of them have been reversed.
Yeah. Well, the fuel standards, there's currently a battle whether California can set higher fuel efficiency standards than the rest of the, and all the automakers, you know, signed on with, yeah, that was sort of shameful. Yeah, all kinds of things have been rolled back. Yeah.
You mentioned earlier that you don't get much resistance from your students.
I haven't, no.
Regarding the science of climate
No,
change.
nobody
I'm wondering if you
debunks
think
me.
if that's because of who you're teaching, who's coming here to UFC, or if you think it's the way you're presenting your information.
You know, we have, I mean, a large fraction of the undergrads here want to major in econ when they get here. And econ department here is you know, they're sort of a traditional, you know, you would expect to find sort of people on the business as usual end of the spectrum in that program. And, you know, they did take my class when I was doing it. So I don't really have an answer. So I was trying to, you know, get them all jazzed up with like adiabatic lapse rates and feedbacks and all that kind of stuff. And they'd be, you know, they'd sort of invest their interest in figuring out how that stuff works. And then I would, you know, I wouldn't lead with the climate change. But no, I've never had anybody try to challenge me, ever. It doesn't happen in public talks either. I don't know why.
I have a couple more questions. What's your impression of this young girl, Greta Thunberg, and the impact she's had? Is it something like the Children's Crusades of the Middle East, Middle Ages, or is she really making some progress in motivating people to deal with these issues? And the other thing, what's wrong with artificial photosynthesis as a means of extracting some of the CO2? I know there's some movement underway to develop artificial leaves to generate hydrogen or biofuels. So is that a viable option, especially what's going on in the rainforest in Brazil?
As to Greta, I, you know, am an observer of American sociology just as everyone else here. I won't go on airplanes myself either because I just can't get past, you know, screwing up the planet for 5,000 generations of people. So she sort of empowered my stubbornness in that regard because she's that way. You know, my family gives me crap, I can just say, well, Greta does it, and they let me alone. You know, she raises it as an intergenerational thing. I've read the idea that our, you know, energy use is a huge case of intergenerational theft, and so she does have authority to speak for, you know, her generation that we don't, I suppose. As for, so artificial leaves, like you mentioned, creating hydrogen or something, that would be an energy source. One of the ideas, actually the mainstream idea that I didn't really mention about cleaning the CO2 out of the atmosphere is to grow biomass, harvest the biomass, burn it, collect the CO2 from the smoke, and use the energy. So this is called biomass energy, carbon capture, and sequestration. And the trouble with that is farmland. So, you know, that's the main way that people put into their planning about how to survive the next century, and it always requires way more farmland than we really have. So that's kind of a no-go. I mean, not a huge idea in my book. Thank you. Go save the world. We need you.